Hi, my name is Ron Bishop, Technical Manager for ID Additives to all things foam. What I want to talk about today is that the test we did with Sumitomo Demag on a living hinge. Okay. Next. So there's really three types of chemical foaming agents. There's a hybrid endo-exo, there's exothermic, and there's endothermic. Just to give you a little background of each one, especially exos and endothermics. Exothermics, heat generating, endothermics, heat absorbing. Exothermic is nitrogen, endothermics is CO2. Exothermics are typically used in extrusion profile. Endothermics, sheet extrusion, injection molding, structural foam molding, blow molding. Basically commodity resins for endothermics. Exothermics is commodity and engineering. Endothermics, engineering as well. Next. Foaming agents for caps and closures. Applications. Potential applications include all types of caps and closures, including those with a living hinge, thicker wall cosmetic closures, and even beverage caps. Area to develop. Benefits to brand owners. As brand owners embrace sustainability and eco-friendly initiatives, chemical foaming agents can be used to reduce a brand's carbon footprint by lowering part weights of their products while maintaining functionality. Benefits to molders. For molders who are striving to better parts and faster cycles, chemical foaming agents can act as a process aid to reduce sink and warp while running at consistently lower cycle times. Next. Equipment considerations for foam, part design, geometry, surface fill, application, speed, multi-component, assembly, production cell concept, new or existing molds, cavitation, resin delivery, mold design, runner systems, gating, single phase, stack, cube, production costs, cycle time, energy, resin, investment, maintenance, special process requirements, decompressing hot runner, balance cavity pressure, process stability, reliability, repeatability, process optimization. Next. Case study. So the test we did was on a living hinge cap. It's a flip top closure, 4 cavity, weight was 10.2 grams with no foam material, polypropylene. The product we used was our ID 6265 70 MFC microfine cell foaming agent. Production efficiency objectives: reduce part weight as much as possible, reduce cycle time, maintain aesthetics and performance of closure. Next. Set benchmark: we molded solid parts without foam at customer qualified 12.3 second cycle time for single component. Chose to mold without colorant, so you can later view the effects of foaming. Observation: we achieved quality parts within spec of overall dimensions. Next. Test procedure: we introduced 1% of foam by weight, ran the foam parts at same setup as benchmark solid parts. What we saw was foam distribution similar to both halves. Internal dimensions were slightly smaller than solid parts. Internal dimensions were almost consistent as solid parts. So what's that's telling you is, because we used no pack pressure, pushing that material as far as it can go and holding it there for 2 seconds, the part shrank. It didn't hold that dimension. It was slightly smaller. We see that in some caps. In some caps, we don't see any issue with that. But in this particular cap, we did see a little bit of a smaller dimension. Next. So when we did different hold times, hold time reduced to 1.8 seconds, 0.4 seconds, and 0. Reduced cycle time as well. What we saw was energy consumption per cycle decreased as hold time decreased, but part temperatures increased. So when you hold it for a little longer period of time, that allows the part to cool under hold time before the gate closes. And then the gate closes and extrudes back. At 0.4 seconds and 0 hold caused parts sticking to center of core since it was too hot. But at 1.2 seconds, hold was okay. And the parts were, obviously, because we weren't packing it, the parts were predictably small. Next. Test procedure. We lowered temperatures, reduced barrel temperatures, mold temperatures, and screw RPM. The reason we lower extruder temperatures is because the foaming agent is changing the viscosity of the material. If the foaming agent changes the viscosity, there's really only one other thing that does, and that's heat. So we recommend you take advantage of the foaming agent, reduce the heat, and you still get the flow because of the viscosity change that the foam gives you. What we saw was maximum part temp drop from 174C to 166C. For 1.8 second hold, energy consumption per cycle decreased by almost 10%. And that's pretty big when you're looking at a lot of machines. 10% reduction is in energy. That's pretty big. Next. So test procedure, we check surface quality. We, looking to mold parts short, molded parts at increasing injection velocity. So what we saw by doing these things, foam resulted in excellent surface quality without sinks, even for really short shots. Started seeing splay at 27 millimeters per second injection rate and slower injection 1 second or slower. Was not able to lighten parts at increased injection rates. And why we're only using 1%. When you go to 1.5%, we could have added more foam and probably brought the weights down a little bit more. But the cost of the foam wouldn't justify the savings that you get. So 1%, you get the best bang for your buck. Every time you add more foam, you add more cost, and then your savings starts to go down. Next. So they were concerned about a living hinge to begin with. So we recommended, absolutely, let's run a living hinge. So check hinge performance, inspected foam at hinge and surface via industrial CT scan. Check molded in stresses with polarized lens. Per customer procedure, open and closed hinge 200 times. So in the picture, you can see we've got cell structure on both sides of the hinge, but none in the hinge. And what happens is, as the foam is flowing through that hinge from a thicker wall, it creates a lot of pressure. So much so that the bubbles can't expand in that hinge. So as soon as it gets past that hinge, you can see that the bubbles are expanding again and they got foam on both sides. What we saw was foam voids do not appear in hinge area, obviously. Solid skin of resin on outer 0.005 inch of part shows that foam does not migrate to the surface. Less molded in stress than solid part, no hinge failures after flexing. See, foam wants to go to the least path of resistance. That's why you don't see splay on the surface. When you inject it slower, what happens is you push the foam to the surface, and that's why you see splay. But typically, foam wants to go to the least path of resistance, and faster velocities make that happen. Next. Next. So this is the financial businesses at the time that we did it. Cost of PP resin, 60 cents a pound. Cost of foaming agents, $2.50 a pound. 1% foaming agent, they added 0.025 cents per pound. At 8% weight reduction, took 0.408 cents per pound out. Material savings of 0.023 cents per pound. Cap without foam was 10.2 grams. Cap with foam was 9.4 grams. Overall is a 4% material cost reduction. Cycle time savings. It started at 12.3 seconds. Ending cycle time was 10.5 seconds. It was a 15% reduction in cycle. We felt like we could probably do a little bit more than that as well. Other savings, less mold and machine wear, less vent cleaning, less cooling water. On a 24 cavity production mold in 1 year, 8,000 production hours, 56 million parts per year, annual savings, 29,000 in material, annual production savings, 1,200 hours. Next. I want to thank Mike Urain, Robert Irwin from NIPRO, Mike from Sumitomo Demag. We appreciate them letting us come in and doing this case study. If anyone has any questions, you can reach out at idadditives.com or reach out to me at rbishop at idadditives.com. Thank you very much for taking the time to watch this. Have a great day.